Let's now try to understand what the sequence z minus n look like. The sequence z minus n is used in the z transform, and we're trying to see how does this z minus n look like when n goes from 0 to infinity. We have already shown that it is a complex exponential, and it depending on different values of z, the complex exponential will change. And in this example, we're going to fix the magnitude of z equals to 1.1 and ej with different omega. Now, in the previous slide, we have seen that when z is a positive number greater than 1, over here, the complex exponential will decay. And the reason that it is decaying is because we are plotting z minus n, which is 1 over zn. And when z has a positive value or greater than 1, then z to the power of n becomes larger and larger in the left hand side. But because it is 1 over a larger and larger number, then the complex exponential is growing smaller and smaller. Now we want to study what the angle omega will do to this rotation of the complex exponential. So let's plot first with the omega equals to 0. When omega equals to 0, then what happened is, let us now expand this. ej0 is equals to cosine 0 plus j sine 0. This is equals to 1 because sine 0 is 0. So we are left with a real number here. So this is 1.1 times 1 is equals to 1.1. So z is 1.1. 1 over z, z minus 1 is equals to 1 over z is equals to 1 over 1.1, which is to the power of n. So z minus n is this expression here. Now we can plot, and you realize that we are only plotting a real sequence because the complex number is always 0, because we are doing omega equals to 0. Right, so take a moment to realize that as n goes to infinity, 1 over 1.1 to the power of n goes to 0. Now, let's study the second one, where we have 1.1 ej 0.125 pi. So we open up ej 0.125 pi and express it as, in the Euler's formula, cosine 0.125 pi plus j 0.125 pi. So this time we are having some real number plus j some real number. Altogether, they are multiplied by 1.1 in the front, and to the power of minus n for z minus n. You work out the values, you will realize that each is a complex exponential that is decaying as n is increasing, and the complex exponential is rotating clockwise. And it is rotating with omega equals to 0.125, which is pi over 8n, implying that it will take 16 steps. 16n steps, n equals to 16, you will complete a complete cycle. So if you count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, then it repeats again. So the omega tells us how fast is the complex exponential rotating. It will take 16 steps to complete 2 pi. What about here? This is pi over 4. It will take 8 steps to complete 2 pi. So let's count 0, 1, 2, 3, 4, 5, 6, 7, and at the 8 steps, it's a line again and it repeats. Of course, because of 1.1 to the power, 1 over 1.1 to the power of n, it becomes smaller and smaller. And if you continue to get this idea, then 1.1 ej is half pi is even faster. At every step, it is rotating by pi over 2. So here, 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 and so on and so forth. So the idea is that as you are using larger and larger omega, the complex exponential is rotating faster and faster. Okay? The interesting thing comes here when we are using omega equals to 1.75 pi or minus 0.25 pi. 1.75 pi is counting the angle anti-clockwise from the positive real. So it will be 0 to pi to 1.5 pi to 1.75 pi until 2 pi here. But you can also use negative angle for clockwise direction. In this particular case, then compare these two plots. These highlighted two plots, they have the same magnitude but different angle. One is a positive angle. One is a positive angle, 1.1 ej 0.25 pi. This is a negative angle, 1.1 ej minus 0.25 pi. Notice the difference. Over here, he's rotating clockwise. Over here, he's rotating anti-clockwise. And they are decaying at the same rate. So this figure here shows the relationships of the complex exponential at different positions in the complex plane. Let's now continue. We will fix the omega and we will now vary the magnitude. Below, this is the blue line, is the unit circle. Below the unit circle are values less than 1. Above the unit circles are values greater than 1. Remember, we are plotting z minus n here. Just now we have plotted this guy, 1.1 to the power of 0.25 pi. What happened as we do 1.2? Meaning 1.2 to the power of n is growing faster, but because we are plotting z minus n, this guy grows smaller, faster than this guy. So if you now understand the idea, as we go to the unit circle, where the value that we are interested in is 1 ej 0.25 pi, you realize that we now is generating actually a complex exponential rotating and never dies. What happened when we go in? 0.9 times exponential 0.25 pi, because it is now less than 1, because and then we have z minus n, the complex exponential is growing. So this is growing quite fast compared to the previous amplitude, which is only rotating with unit circle, but here it is at 50 now for the amplitude. And when we make it even smaller, it is growing even faster. So the take-home message is this: the magnitude will determine the growth rate of the complex exponential. The angle will determine whether it is rotating clockwise or anti-clockwise. This is the code to do that. So I'll just leave it here and you guys can play with it. It's only the following lines to generate the plots. I'm going to leave some reference of complex inner product. You do not really need to understand this, but it'll be nice if you do so. And here is complex inner product definition, where x is the vector, y is another vector. The second slot is complex conjugated. And this is called the Hermitian inner product. Thank you.